All right, just messing around here a little bit as we wait for some more people to enter the live stream. And if you're joining us now, we're just giving a couple of minutes for a few other people to come on into the live stream. Until then, I'm just going to show you what we're going to be doing today. We're going to be building this little kind of tower, self-replicating tower thing, and then we'll learn how to kind of get this visual look as well. But it's pretty fun. There's a lot we can do with this with this kind of idea. So we'll give it a couple more minutes, and then we'll get the stream started. Until then, I will keep messing around with this. All right. Okay. So how are you going to build this? So the fundamental thing is here, when I hit stop, you're going to see that it all kind of starts with this little cube. And from here, we can kind of build up to this entire kind of thing that we were seeing a second ago. And so I'm going to go through this very step by step. We're going to actually, this is really the main part of this lesson is going to be kind of a deeper dive into Lua. So we're going to understand a little bit about how it works, and I'm going to go very slowly and take questions if anybody has questions, and really break this down. But it's very straightforward, and the results are really cool, and it's very additive. You can do lots of interesting things with this idea. Okay, so I'm going to do File New. We'll start fresh so that you can follow along. So when we do File New in Simmetri, when we just start the app, we're always placing this kind of planetary surface world. And this is kind of a fun place to play and just test out ideas. But it obviously comes with a particular look, and we can go and change all the textures and change it visually if we want. But it's actually much easier to get a quote-unquote look if we just start with an empty blank space. So we'll get out of this planetary surface space. And so to do this, I'm just going to right-click on the browser and create a new open space. And then I just double-click on that. And that puts us in this kind of empty black void that's now much more abstract, and we can kind of build from here a much more complete visual style. So the first thing we're going to do to build this little crazy tower building thing is just to build a simple box. This is going to be our replicating object. And so I'm just going to literally go in here and just draw a box. And the other thing I'm going to do is, for our purposes for now, is I want to just make sure that it's numerically kind of simple. So I'm going to just double click on that box. I'm going to just set its dimensions to be 1 by 1 by 1. And we'll start here, and then later on we'll adapt it so it will automatically adapt to whatever the dimensions are. But for now, let's start simple and make it a 1 by 1 by 1 cube. So the first thing we want to just do is figure out a way to make this, using script, how can we make this cube replicate? And these kind of ideas, whenever you have something that just you make a copy of, it's super useful. I mean, like imagine something colliding with it and it breaks into multiple pieces. And you know, this idea is really like common in terms of things that you want to be able to do as part of your tool belt of things that you might want to be able to do when you're building a scene. So what I'm going to do right now is I'm going to implement I'm going to add some script to this object. And so I'm going to go to the box entity, and on events, I'm just going to click on init. So this is script that gets called whenever this object is initialized. Like when we hit play, this script gets called. This onInit function gets called. But we're not going to actually implement onInit yet. We're going to actually implement a function that is going to that when we call this will replicate our cube. So I'm just going to create a function that lives in this object called replicate. And basically this function, whenever this function gets called, we're going to replicate ourselves. And then that's it. Every cube is just going to worry about replicating itself once, and then it never worries again after that. So all we have to really do is just replicate ourselves once. And so a very straightforward way to replicate, before we go into choosing a random direction and all that other stuff that from the final kind of product that you saw, we're just going to have it simply replicate along one axis. Just a really simple example. So what I'm going to do is I'm going to say self clone as shared copy. And we're going to store that in a variable called copy. So this will clone ourselves, and it'll clone it as a shared copy. And I'll get into a little bit more why there's two versions of clone as copy and clone as shared copy. We want to use a shared copy in this case because it'll make things a little bit more efficient. So we're going to call clone as shared copy. That's going to return the copy in this variable called copy. And then we're going to just set our world position. And in this case, I'm just going to do set world position. So our copy is going to be placed somewhere. And we're going to place it next to us. So I'm going to say self get world position. And I'm going to add an offset. And in this case, I'm adding an offset along the 1, 0, 0 axis of this object. So in other words, we're adding 1 along the x-axis, but nothing along the height and nothing along the z-axis. So we're just taking our current position of this current cube, and we're just going to add this this offset, basically, this 1 unit in the x direction, x, y, z. And then we're setting the copy's position to be that. So if we hit play, actually nothing's going to happen because we're not calling this function anywhere. So hit play, nothing happens. So the first thing we're going to want to do is on init. In here, we're going to create a timer. Now you got to be careful. If we call replicate in on init, it will just get stuck in an infinite loop right away because it's going to call replicate. It's going to make a copy, which is then going to call on init on the new copy and so forth, and it's just going to get stuck in an infinite loop. So we don't want to do that. We want to create a little bit of a delay, because then that will allow us to kind of hit play, see it kind of evolve, and then control for complexity later. So to create a timer, and we introduced this in a couple of previous tutorials, I'm just going to say get animator, which is a global function. You can call this from anywhere. I'm going to call create timer self on our self. This is the function that we want to call, and it's going to be replicate. And we're going to wait a certain amount of time. So we're going to wait maybe 1/10 of a second. So what this is going to do is when this object initializes, i.e. when we hit play, this on init gets called. It then says, okay, I'm going to create a timer that's going to wait 1/10 of a second. And then after 1/10 of a second, I'm going to call this replicate function, which is then going to go ahead and make a copy of ourselves and place that copy to the right of the cube. And one other thing we're going to do is we're going to make the rigid body of this cube to be non-movable. If we make it movable, then it will self-displace itself. It potentially will be able to move, and we'll do that later. But for now, let's make movability of this object to false. That means it stays in place. In this open space, gravity is 0, 0, 0. There is no gravity, so everything kind of floats. But for now, we'll keep everything fixed. Okay, so hit play and see what happens here. Oops, I have a typo here. This should be a vector 3. Hit play, and there it goes. It starts replicating. And since we set our object to be exactly 1, 1, 1, its dimensions, our offset is exactly 1 in this case. If we made this 1.1, for instance, it would offset it and put a little space between all of them. So now we have kind of an idea of how we can replicate an object using a very simple script here. We just create a timer, and after a little bit of time, it copies itself, and then it's done. It doesn't have to worry about itself anymore. And then the next object repeats that process, and it kind of goes on forever. And so what we really want to do is we want to call this replication logic, but we want to pick a random direction so that maybe it will go up, maybe it'll go this direction, maybe it'll go in this direction. I think it'll create a much more interesting look. So how do we do that? So the first thing we want to do is we're going to basically ask a random number generator, give me a random side, 1 to 6. And so in Lua, the way we do this, we say math.random and 1 to 6. And so this is going to return a number that's between 1 and 6 using a pseudo-random number generator. And that will return a value inside. So we either get 1 through 6. And so now using that number, we can pick a side, pick a random side. Now you notice that the way we this is the positive x direction. And so you can imagine the negative side would be -1, and then we could go up by going 0, 1, 0, and so forth. So we can permute all these different cases. There's 6 different cases of various 1, 0, 0, 0, 1, 0, and so forth, -1, 0, 0, to choose a side. And so to do this, I'm just going to build a little table here. This is going to be a table of sides. And I'm going to initialize this table to all of our possibilities. So table sides at 1 is going to equal to vector 3, 1, 0, 0, and I'm going to copy this for 6 sides, and I'm going to make sure in our array, we choose each one, and I'm just going to create a permutation of all these. So I'm going to do 1, 0, 0, 1. Then we're going to do -1, 0, 0, 0, -1, and 0, 0, -1. So by adding this vector to our object's position, we essentially can either we can go in any one of the 6 directions of the cube. And since we're now choosing a random side, we can now use this side value that's returned as the index into this table, and that will return us one of these random sides that we can then add instead of doing this here. So I'm going to create a little function that we can just call. This is a little bit a cleaner way of doing this. It's going to be get a side. I'm going to pass in the side number, and we're just going to return from our table of sides the value that we ask for it, being 1 to 6. So it's going to literally just go in here and index 1 to 6, one of these, and it's going to return one of these. So once we have that, we're going to literally say our v offset is equal to self::get side. And actually, we don't even have to. We don't have to make this. We can actually make this a global function. Like we can. So if it lives inside the mesh entity, then it's like it's per instance. But if we just make the function global like this, it lives. All of the different objects that we make copies will share the same function. Long story short, this is just a cleaner, simpler way to do this. So I don't have to call self in the object. So I'm literally going to say get side. We're going to pass in our random 1 to 6 value, and that's going to return our offset. And then instead of adding in the original vector that we added in here, I'm just going to pass in this offset. So now it's going to add. It's going to basically choose a random angle, random side every time we hit play. So let's see what happens. And there we go. Now we have this funky little kind of self-building boxy thing. Pretty straightforward. Nothing too bad here. So we can keep building up on this example. So what are some of the other things we could potentially do? Well, one other thing we might want to do is, and as you saw in the original example, is maybe wait a little bit of time and then cause it to become movable so that it crumbles, basically. And so how do we do that? Well, just like we created a timer when it initialized that then waits to create a replication to call this function, we can also create a timer that will wait a little bit of time and then mutate one of its properties, namely the movability property of its physics, of its rigid body. So that means after a couple of seconds, it will then become movable. So wherever it happens to be, it will fall down, or we'll make it move in some particular direction. So let's do that. So we're going to say get animator, a global function, and we're going to say create timer. And we're going to say on ourself, we're going to call a function called self.crumble. And we're going to wait a certain amount of time. Maybe we'll have it wait maybe 7 seconds. We'll have it wait a bit so it gets nice and develop the tower before it crumbles. And then we're going to implement a crumble function, entity::crumble. And then basically here, what we want to do is we want to change our movability. So we're going to say self::get a rigid body. That's just going to return this object right here. So this is the self, is the box entity itself. And get rigid body is going to return this object here. And we're going to set movability to true. So we're going to say get rigid body dot movable is equal to true. Now, the one thing you're going to have to, one thing we have to explain here is when we do this, since we're making shared copies, all of the copies share the same property value. So I'm going to make a copy of this now so I can kind of demonstrate this. So if I take this object here and I make a shared copy of this, which is what's happening when our script is running, all of these now are shared copies of one another. Watch what happens when we go and we change one of its properties. So I go here and I change the active property. They all have their active properties set to the same exact value. So that's one of the things that shared copies do, is they all share the same values, the same properties, which is really good from the standpoint of efficiency. It means that we only have to kind of sample one set of data that kind of is per object, basically. So each object has some local data, but they share a lot of the same underlying data structures, and that makes things more efficient. But the penalty of that is that they have to share the same properties in this case. So in the case of a rigid body, the movability, we want them to individually be set to movable to true. We don't want them to, as soon as we set that property, all of them would become movable, and that's not what we want. We want the last one that was replicated to become movable, and then future ones become movable as we set them. And so to do this, all we have to do is go into our original box. So to go to the rigid body, and we're going to detach this property here. So this movable property, we go over to this little button up here. We can say detach from shared copies. Now that means we can set this property per object. So they're all shared copies, so they share the same property. They share the same shape. They share the same all these properties. But the movability now can be set individually for each one. So the only other thing we have to do is we have to set some gravity for this space, because if we don't, as soon as they become movable, they're just going to float in place. And so I'm just going to click on the space anywhere, and I'm going to click on the open space here, and I'm going to go under physics, gravity, and I'm just going to set this, maybe instead of having them fall down, I'll just set like a horizontal gravity, so they kind of move horizontally. Okay, so let's review what's going to happen. Object gets on play, the object initializes, so it creates this timer, which waits 1/10 of a second, which then replicates the object, choosing this random side, positions it, and then basically calls on itself. So the current object that it replicated from, after 7 seconds, it's going to become movable, and then the next object will repeat that process. So let's see what happens. So we're going to wait 7 seconds. I'm going to hide the grid for now. And there we go. After 7 seconds, they slowly become movable. So now we have this kind of interesting dynamic effect, which is pretty neat. So let's work on the visual style of this, because this is a little boring. This is like the standard kind of. I'm going to close the script for now. So one of the things I like to do in these kind of abstract spaces, I'd like to switch the blend mode to make it additive. So I'm going to click on this object, and I'm going to go and find its material. So under box entity, mesh model material, it's currently using this default material. I'm just going to click on that, and then under translucency, I'm going to set its blend mode to additive. And additive is neat because as they overlap, you get this kind of neat additive look like that. And I think that kind of looks kind of neat. And so let's see what that looks like when it starts replicating. So that's already kind of neat. We got this kind of interesting, kind of almost, I don't know how to describe it, almost abstract-y kind of interesting kind of a look. One other thing we could also do is change the color each time they're copied. So I'm going to go back into the object here. Actually, so before we do that, we're going to have to detach the color property. So just like we did with the rigid body, we had to detach the movability property because we're going to be setting that individually for every object. We also have to do that to the color property, or else they're all going to share the same property. In fact, let's do it without detaching it so you can kind of see what I mean. So back in the code of the object, whenever it's copied, I'm going to set a color value on the copy as well. So I'm going to say copy.color is equal to, and then this is our RGBA function, which is the classic 0 to 255. We specify per channel, but we want to randomize it. So I'm just going to say math.random 1 to 255, or 0 to 255. So that's going to choose a random value from 0 to 255. And then we can do the same thing, maybe not for the blue channel, we'll do it for the green channel. That will kind of limit our palette so that we don't have too many crazy colors. So watch what happens. Since we didn't detach the color value, that means whenever a copy is made, we're setting the color, but they're all sharing the same color, which could be cool. Let's see what happens. So notice that it does that, but we want them to individually have the same color because, again, because they're shared copies, they all share that same color value. So this color value is being set for one of them, and then they're all sharing it, so it's overwriting it. So all we have to do, just like we did with the rigid body movable, is we just have to go and detach it by clicking this and detach. And now they'll each have their own individual color. So now we can keep kind of building on this example, and we can keep kind of messing around with it a little bit. Another thing I like to do is I like to add filters, image filters. So I'm going to click on this open space viewport, and I'm going to add a new image filter. And I'm going to add this sketchy image filter, which kind of creates this almost like paper look, which is kind of neat. The only thing here with this look is we kind of lose the colors of the original cube, but the color still comes through in terms of its brightness, and so we still have some variance there. And then I just like to play around with maybe the colors of this gradient map and kind of give it like a black and white kind of color is nice. You can play around with all the different parts here to create different effects here. We can just do that. I kind of like almost a black and white look. Okay, so now we have kind of an interesting little effect here. So one thing we can also do is speed up this animation. So I'm going to right click and go back into the script. And so initially we set this on init timer code to be 1/10 of a second. So that's how long it waits before replicating the next cube. If we make it 1/100th of a second, this will replicate much faster now. But it'll still wait 7 seconds before it will detach. Another thing we could do is we could have it wait a random amount of time maybe. And so instead of going 7 seconds, we're going to just say math.random. And maybe we have it wait between 2 and 6 seconds. So some will detach much faster, some will crumble much faster than others. So let's see what happens. So some are crumbling, others are waiting, or getting stuck behind the previous ones. That's a little bit more like interesting. So another thing we might want to do is make this a little bit more dynamic. So right now we kind of hard-coded into our code to use basically this offset, which assumes 1. Basically, 1 is our value, which is convenient because our box is exactly 1 by 1 by 1, and so it's an exact. That offset is exactly what we need to kind of step in every direction exactly as we expect. Now, what if we wanted to make changes to this value? Well, our code is still internally making a 1 as an offset, so they're going to kind of overlap incorrectly now. That's not what we want. I mean, it's still pretty neat, but I think what we want is we want it to have to step exactly along that axis, whatever the dimensions of the object, whatever they are. And so to do this, we just have to query our dimensions and then offset ourselves by those dimensions. So I'm just going to say self :get mesh model :get shape, and what we're just doing here is we're just saying self is the box entity. This is where the code lives, and we're just saying get my mesh model. Then I'm going to get my shape, and then I'm going to get the dimensions basically. Dimensions. I'm going to store that in a variable called dim. And then we just need to multiply our side. This is the value that's here by this dimension. So it's essentially going to scale these 3 numbers by the equivalent value that lives in the dimension. So I'm just going to take a side, and I'm going to, so this is going to return that side, that vector, and I'm just going to multiply that by the dimensions. So this is going to be identical now. You're not going to see any change. But if I go and make changes to this, let's say we make it long instead of, now it will step correctly along that direction. So it fills out the space really nicely. So we start getting these kind of interesting abstract kind of looks. If I was to make and really exaggerate this, we can make it like really long. And now we get these really interesting, along that axis, you get this kind of interesting effect. But I prefer it a little bit smaller. Well, for the purposes now, for this next demonstration, we'll keep it at 1 by 1 by 1. And then we'll play around with that dimension a little bit later again. Okay, so another thing you might notice is, you might ask is, this is neat, but it looks like there's a little bit of overlap going on, and you'd be totally right. Right now what I'm going to do, I just paused it, and I'm going into, there's actually a little trick here. If you go view, you can say lock playtime generated objects. You can kind of remove that. It's turned on by default. If I remove it, I can now select these objects. And if we look carefully, we'll see that in some cases there's actually 2 objects or 3 or more that are overlapping the same cube. And the reason why is that the random generator, it doesn't know if it's coming from a direction that it's already visited. So it may just recopy itself back to the original direction. So in other words, when this decides to make a copy, it'll make a copy here, and then when this one decides to make a copy, maybe it goes back on top of the original one. And so what happens is we get these overlaps. And I think in this case we don't really care that much because we have this additive effect. It's nice that it does it. I don't think it necessarily detracts from it. But let's say you did want it to be perfect so that everything is non-overlapped. How would we go about doing that? Well, to do that, we're going to go back into the script. So this is a little bit more involved, but I think it's super useful because what it allows us to do is to build these kind of perfect spaces where everything can inhabit exactly 1 point in this space. And it might make this effect look a little bit nicer. So to do this, we have to build what's referred to as a hash table. Basically, a hash table is nothing more than just a thing that we can ask to basically say, has something already been at this place in space? Or not necessarily a place in space, has something already registered itself with this particular entry. So think of like a keyboard, like a piano, and if I hold down a key, I can't press that note again because I'm holding down that key. The key played once, and if somebody else comes around and says, I want to play that key, well, they can see that my finger is holding it down. So therefore, we've officially accounted for it, that it's being held down, and nobody else can press that key. So that's basically what a hash table is. And what we're going to do is we have to basically find a way to make our position in space map to this hash table. So I'm going to build a little hash table, which I'm going to refer to as visited. This is a table that basically says, I'm going to ask it, has somebody been visited? Has a particular point in space been visited already by a cube? And if so, I can ignore it and try again and try a different random direction. And now we're going to create little functions here that are going to allow us to kind of query and set our table. So I'm going to say, I'm going to create a function here called mesh entity. I'm going to call this isVisited. So we're going to call this, actually we can make this again, actually this is very important. We're going to make this global. We're not going to make this inside the mesh entity, inside the table itself. This function, we need it to be shared across all of our copies. So all of our copies are going to share this table. This is important because they all have to refer to that same hash table. They all have to kind of point at the same table that says, are we inside, has anybody visited this particular point in space? So we could have, for instance, if we had created the table like this would be per instance. That means every copy would have its own table. We don't want that. We want them to all share the same table. So we just create it globally like this. And then what we're going to do is we're going to create a function called isVisited. Oh, sorry, there we go again. Force of habit. And we're going to pass into this isVisited function a vector, which is going to correspond to our position, our new position, basically. So now what we want to do is, given that position, we want to ask, has this position in space been visited so that we can avoid visiting it again? So what we have to basically do is, this is going to be a vector 3, right? So we're going to be passing in a vector 3. We're going to be passing in its world space, its world position into this function. But that doesn't necessarily map to an entry. We need to convert that vector 3 into a unique value that, given the same vector 3, so if it's like 1, 0, 0, it will always map to a unique number inside our table. And so we have to come up with a hashing function for that vector 3. So I'm just going to create a little hashing function. We're going to call it hash, and it's going to take in, and I'll explain this a little bit better after this is done. So what we're going to basically do is, we know that this v value is going to be a 3-dimensional vector. We have to basically convert this into a single value, a single number that we can then plug into a table like this. So I'm just going to write something really dumb here, and there are a lot of different ways you can write hash tables and hashing functions for positions in space, and there's much better ways to do it than this. This is just a quick and dirty way of doing it. I'm going to just take the x value, I'm going to add like an offset, and then I'm going to multiply it by the y value. I'm going to just add some other random offset, and usually what you do is you use prime numbers and a bunch of other tricks to kind of ensure that the distribution of the hash values is uniform, but in this case this is not going to be very well distributed. And I'm going to just multiply that, or add this to like another value here. It doesn't really matter what it is. So let's see what this is going to return. This is going to take our 3-dimensional vector, our xyz value, which is one of these basically, that's then been where we've actually calculated the real position. So we've taken the world position, and then we've added in that offset. We're going to take that unique position in space, we're going to pass it into this hash function, and it's going to return a unique value, a unique-ish value. Based on the x value, the y value, and the z value, is going to produce a single number, which we're going to then plug into our table. And then in that table, in that entry, we're going to be able to determine if somebody else is visited. If somebody else plugs in the same vector 3, we're going to be able to see that, oh, no, somebody else has visited this. This has already entered the entry inside the table. And so what we're going to do here is just simply say, if our table visited at our hashed value, we convert that vector 3 into a single number. If it's true, then we're going to return true. Actually, we can just simply return. Yeah, we can just return with that what's in that hash table directly. So what this is just simply doing is saying if it's returning whatever's inside that table. If there's nothing in that value, it's going to return nil actually, or false. If there is something there, we're going to write true when something is visited. It'll return true. And so now we can ask for a particular point in space. Has this point in space been visited? And then the other thing we need to do is we need a function that lets us make that account to actually go into that table and set the value. So we're going to say set visited. This is going to take our vector 3, whatever that position in space is, and our value that we're going to set. So it's either going to be true or false. And we're going to say table visited using our hashed value is equal to value. So once we determine that we haven't visited and we actually make that copy of the object, we can then account for it inside our table. So then the next person that asks, has that position been visited, will be able to find out from the table that somebody has already visited it. Let me try another location. So right now our random number generator here is always choosing a side and just committing itself to that side. So we have to basically say, no, we need to check. We need to repeat and keep checking until we find a side that hasn't been visited. So we're going to use a repeat loop here, and we're going to say until it's not visited. So we're going to say if is not visited, and this is going to be our position in space. So what we have to do here is after we calculate our offset, we want to take our self world position pre-added in. So I'm actually going to just move that all into here. So this is going to calculate our current position plus our randomized side, and it's going to store in that v offset. Now we can ask, okay, we're going to keep looping until we find a point in space that has not been visited. And so so when we exit this loop, we'll know that this v offset has not been visited, and we can set our world position to that location. Now, the one thing you have to be kind of a little wary about is whenever you have a loop that kind of relies on the result of a random number generator, you run the risk that it may keep getting heads basically. Maybe it rolls the dice and it keeps getting 1, 1, 1, 1, 1, 1, and this could potentially go on forever. It's unlikely that it would get that more than a certain number of times, but it could happen. And so we have to also build in a little bit of a short circuit here to ensure that that doesn't happen. And so actually what I'm going to do is I'm not going to implement that, and we'll see if it blocks, if it ever gets stuck in a case. Because there's actually another thing that's going to happen here is that since this is not a perfect hash function, there are going to be multiple vectors that are going to return the same value, right? You can imagine different, if you permute these in different ways, there's going to be, I can pass in 2 different vectors that have very different numbers in their components, but they actually, after doing this really simple little formula here, will return the same value. Which means we might get stuck in a case where we keep asking, has this been visited? And even though there's nobody there, or it will still say yes because this hashing function is returning that somebody is already there. And so let's see what happens if we hit play here. Let's see if it actually gets blocked. So I'm going to go ahead and hit play here. I'll zoom out here. And okay, so it seems like it's going okay. I'm going to actually hit pause here, and let's just sanity check here to make sure that there are no duplicates here and see that our hashing function is working correctly. So I'm going to go here and just move around some of these boxes. And I think that one was okay. I don't think there was anybody over there. Not sure if that was at the right angle here. Oh, no, it looks like it did not work. Oh, right. So there's another reason why that's not working. We didn't account for it. So right now we're simply asking, but we're not actually going in and setting the value. So we also have to make sure we go in and set that value. So I'm going to say set visited for our offset is true. So we're going to go in and once we visited, we got to go and make sure we actually set that value to true so that future people who are copying know that hasn't been visited. Okay, let's see if that works. Go find my cube again, play. Okay, so you can see now it's much lighter looking. You can tell that there's less overlaps. And I'm going to just sanity check, hit space here, stop the world, and let's just pick a random cube. Yep, no overlap, no overlap, no overlap, no overlap on that, no overlap on that. The opacities here are just because of the different colors. But we can pick any out here, and you can see that there's no overlap now. So we have a nice, unique set of cubes now. We've gotten rid of all the overlap cases. But let's see if we can get this to freeze, because our hashing function is not perfect. So there's potentials for people saying, oh, no, there's somebody already there, and then random generate another one. Oh, there's somebody already there, and it may potentially get blocked. So let's see if it happens. And well, if so, we'll make it more robust. Aha, there we go. So it's entered a case. If I escape now, it's entered a case here, and I can kind of step in and see what's going on here, where it's basically stuck inside this loop. This loop is just, it's like, oh, no, give me a random side. Oh, it's the same side. Nope, somebody's already there. Give me another random side. Nope, somebody's already there. This is two reasons why a random number generator may just keep returning 1. And the other case is our hashing function isn't perfect. So we just need to build in a little kind of, if worst case scenario happens and you get stuck in this loop, let's just exit out. It just means that we're going to end up making a copy on top of an existing one, but we're okay with that. I think it looks fine. So we're going to go ahead and just put this little like short circuiter basically here. I'm going to say total is equal to 0, and then I'm going to say total equal to total plus 1. So as we're iterating over this, we're going to see this total value increasing, and then we're going to basically repeat until either we visited something that hasn't been visited, or our total happens to go above 6. So we in this case, or 10, it doesn't really matter. The smaller the better. So it's going to try 6 times, and if every single time there's somebody there, and the random number generator just keeps giving the same value or whatever, we're just going to exit out and make a copy and just say, it's fine. It'll just overlap in that case. I think we're okay with that if it happens. But in this case, it won't block. So we hit play, and this should just kind of go on forever now without ever really blocking. So now we have a much more robust kind of way of letting this kind of go on indefinitely without potentially causing blocking issues. That's pretty neat. We can keep adjusting this. So back to this now, we can kind of make these long. And so one other thing we're going to want to do is we're also going to want to make sure that these things get removed from the space. And so right now, they're going to kind of live on forever, and that's a problem. As we get more and more, we're going to eventually want to kind of make sure they go away, so we don't have an infinite number of things that are just building up. So to do that, inside our crumble function, when we set it to movable and it starts like moving the space, we're also going to just orphan ourselves eventually. So we're going to say self : fade out and orphan. That just means orphan means remove it from the space. And the first parameter of this is how long do you want to wait before removing it from the space. And we can wait like, I don't know, 10 seconds, or maybe like 8 seconds. So it's going to wait 8 seconds and it's going to remove it. So it's going to crumble, it's going to fly through the air, and then after 8 seconds, it'll remove itself. So now we have a nice, robust kind of thing that can kind of go on indefinitely. without any major. So let's see what happens as we follow these falling boxes here. You'll see that at the end they will eventually fade out, and you can see them fading out there. So now we have a nice kind of constantly repeating example here where they will eventually remove themselves. It's nice and efficient. They don't overlap because we have that hashing table thing, although that we didn't really need that, but it just makes it a little bit more cleaner. And we can keep going. So the neat thing is that we can take this and we just make a copy of this, for instance. And now that will have its own tower, which is neat. So we can have these dueling kind of towers here. I'm going to keep maybe messing around with the visual style a little bit. We can maybe make this additive here, get those colors back in. What else? You can do all sorts of things here. You can maybe make this a little blurry, or maybe put another edge detector in there. No, that's weird looking. Let's see here. Sharpen. It's kind of interesting. It's a little sharp here. Maybe we can downsample this, see what happens. Oh, that's weird. Make it pixely. Maybe make it normal now, or like pixely. That doesn't look very good. But we can keep really messing around with the visual style of this. I'm going to actually revert that back. That doesn't look very good. Interesting, but doesn't look very good. Okay, so another thing you might want to do is, well, let's say we're in VR and we want to grab these things. We want to do something interesting in VR. So how would we do that? Well, what we can just do is we can assign to this thing a interaction. So we can make them, for instance, grabbable, fixed, and just click on it. So now every time this thing is made, a copy is made, it also will have with it this property of grabbability. So I'm going to create also a VR rig in here, VR, AR, VR preset, sticking this somewhere on the floor, and this will allow, we'll fly around in this space here. So we'll fly toward this and we'll be able to grab them in midair here. So I'm going to go into VR mode. Okay, and let's see what happens here. Oh, right. And so one other thing, so the VR rig creates a new viewport, and so our current image filter lives on this open space viewport, but the VR rig has its own viewport, so we don't have that image filter. So I'm just going to recreate that image filter on here. Image filter, gradient map, and then I just set this color to be white, and this color to be black. Oh no, sorry, I did a sketchy. And then I set this to be black. Or no, this white, and this to be black. Okay, so now our image, both our viewport that we're looking through the HMD and the space have that same filter. So okay, back into VR. Let's see what happens when we grab these things. So now we can kind of fly around. We can actually grab these, and these are stuck. And then over time, they're going to get made into movable. Just kind of neat. So we have these, so we can either grab them in mid-air as they fly. Oh, got that one. Put that on its way. And we get this kind of interesting effect here. So that's a pretty straightforward thing to do there as well, is just make the VR, we can add these VR properties and then be able to actually interact with these things. Other interesting things here, other fun stuff to do in these kind of things is kind of play around with, like, because physics is enabled, we can build like all sorts of interesting things here to like block them. So if I make this movable to false, as they kind of become movable, you can interestingly kind of put like a giant wall in front of them, which is kind of neat, and create these interesting flows. I'll make this bigger here. So you get all sorts of interesting patterns, and whenever you have these kind of dynamic spaces, it's fun to kind of see what happens as you create other things in these spaces. So I think I was playing around with this too before. Let's see here. Tricky. You don't have a lot of perspective in terms of determining where you are with respect to the space in here, because you don't have a lot of like frames of reference. We can try to like capture these tubes. We can try to capture these things to our tubes here. And again, I like this kind of additive effect. It creates this really nice kind of overlapping, kind of vortex-y kind of thing, which is kind of neat. So it's very quickly kind of build up a lot of interesting visual styles in this type of space. And then this little replication example really allows you to kind of do things really quickly and get some really neat things going. So let me check. I see John. John, you have asked a question. You could get trapped with that. Yes, indeed. Yeah, so you could have all sorts of interesting ideas in terms of getting trapped, and maybe, maybe part of the game knows structurally kind of where you are, and it tries to envelop you. I think there's a lot of interesting ideas. It's like the end of Infinity War. Navigate to the inside of a 3x3 and be surrounded by stuff. Yeah, I agree. Yeah, there's all sorts of possibilities, I think. But yeah, I think, from here you can really kind of mess around and really go and try things by select these here and move them. Kind of create this interesting, strange world here. Well, I hope you enjoyed this example. I'm going to be sharing this on Steam, so you'll be able to download this and mess around with it yourself if you want to play around with this space. And if you're joining us outside of Discord, you should go to Learn, join the Simmetry Discord channel to join us here. We're always there responding to people's queries. We're always happy to help people as they learn the tool and answer any questions you might have. Thanks for watching, and I'll post this show imminently inside the Discord channel. See you next time.